Welcome. This video addresses section 2.3, computing limits. In the previous two sections, we have seen limits and how we've seen the idea of limit and how they are important. And in this section, we get into the nitty-gritty of actually computing them. A couple techniques for computing, what I call looking for holes and the factor fact, and continuity. Those two observations lead us to the ability to actually compute limits. And in the very end, I talk about a little bit of theory with the limit laws. Holes in graphs. Sometimes it happens that there is a graph that has just one point missing from it. On the right, this is the graph of the function g of x equals x squared plus 1. It looks like a parabola and it's shifted up 1 unit. Nice, standard, completely filled in line. On the left, it's x squared plus 1, but I multiply times a factor of x minus 1, and I divide by a factor of x minus 1. Look at the effect of that. If I plug in 1 into my function, I get 0 in the denominator. But, and here is the key idea, as long as x isn't 1, these two functions are exactly the same. So f of x, I'll just write that down, equals g of x for all x that is not actually equal to 1. And what is the effect of that on the limit? The limit as x approaches 1. Well, as x approaches 1 from the left in f, that's exactly the same thing as when x approaches 1 in the function g. And when x approaches 1 from the right in f, those values are going to be exactly the same as when x approaches 1 from the right in g. Because in limits, we don't let the x actually take on the limiting value. X just approaches that value. So, the limit as x approaches 1 of f of x has to be the same as the limit as x approaches 1 of g of x, because x is never actually equal to 1. And when x isn't 1, then these two functions are the same. Now just look at these two functions as problems. If you had to figure out the limit as that guy approaches 1, or if you had to figure out the limit of that guy as it approaches 1, well, you'd want the one on the right. It looks simpler. So canceling those common factors gives us a simpler problem to work with that has the same limit. Here's another example. On the right, here's the function 2 to the x. On the left, 2 to the x times x minus 1 divided by x minus 1. Suppose I wanted to take the limit as x approaches 1 of the left-hand side. Well, as long as x isn't 1, these two functions are the same. So the limit as x approaches 1 of 2 to the x times x minus 1 divided by x minus 1 really is the same as the limit as x approaches 1 of 2 to the x. Canceling these common factors doesn't change the limit, and it gives us a simpler problem to work with. So this is a really nice tool for simplifying limit problems. I know that I can cancel common factors without changing the answer. One last example here. I have a sine function. I can put a hole above the x value pi over 2 simply by multiplying by x minus pi over 2 and dividing by x minus pi over 2. And that looks exactly like the sine graph, except at the point x over 2. And so, just visually looking at these two things, it looks like that limit problem on the right is certainly an easier problem, and it is. And I get there simply by canceling common factors. So canceling common factors on the top and the bottom doesn't change the answer to the limit problem. And that's what I call the factor fact. The limit as x approaches a of g of x times x minus a divided by x minus a equals the limit as x goes to a of g of x. Canceling common factors does not change the limit. This allows us to simplify limit problems. Now, it doesn't let us solve it. This is just the first step in solving a limit problem, but it allows us to simplify the limit problem. Here's an example. The limit as x goes to 5 of all that stuff. And it looks like a pretty complicated problem, but I notice that I can factor the numerator. And when I factor the numerator, look at that. It looks like I have a common factor on the top and the bottom of x minus 5. those factors can go away, and I'm left with the simpler problem of the limit as x goes to 5 of x plus 7. Doesn't that look like a much simpler problem to try to solve? All right, now let's talk about how to go on to the next step to actually compute the limit once I've simplified. And here's an important idea that every, say, calculus function, let me say like 99% of the functions that we will encounter in calculus class, these calculus functions are continuous on their domains. Here's what that means. Take a look at the graph there. That function is generally continuous, but something weird happens at 3. But on the other hand, what is the domain of this function? The domain of the function is the set of all x such that x is not 3. So as long as x isn't 3, the function is continuous. For example, what about at x equals 5? Look at that. I go to 5, I go up to the curve, put a dot on the curve, and the curve goes nice and smoothly right through that point. The function is continuous at 5. Or what about 2.5? I go to 2.5, I go up, I put a point on the line, and look at that. That curve is nice and smooth right through the point. So, as long as I consider only points in the domain of the function, then that function is continuous at those points. And that's what this expression says. If a is in the domain of f of x, then the limit as x approaches a of f of x actually equals f of a. That is, the curve goes nice and smoothly right through the points. You might call this the plug-in principle. In order to evaluate the limit, I simply plug in the value of a. Here's how it works. So 4 is in the domain of this function f of x, which is 5 over x minus 1. And I know it's in the domain because if I plug in 4 for x, I don't get anything weird. That denominator doesn't become 0. I just get some number out. So if I want to compute the limit as x goes to 4 of 5 over x minus 1, all I have to do is actually plug in the value of 4 for x. Since 4 is in the domain of the function, I can plug it in to find the limiting value. Consider the function 2 to the x. 12 is in the domain of this function, right? If I plug in 12, nothing crazy goes on. So the limit as x goes to 12 of 2 to the x is 2 to the 12th. Negative 7 is in the domain of 1 over x. And so if I have my limit problem, the limit as x goes to negative 7 of 1 over x, the answer is 1 over negative 7. Now, 3 is not in the domain of 1 over x minus 3. You can see that, right? So we cannot evaluate the limit as x goes to 3 of 1 over x minus 3 by plugging it in. Okay, the plug-in trick is not going to work in this case. 5 is not in the domain of this function. So I can't evaluate that function simply by plugging 5 in. Now this one's a little bit weird, right? Because this actually does have a limit. It actually does have a limit as x goes to 5. But I just can't use the plug-in trick to find that limit. We can't plug in to evaluate its limit as x goes to 5. All right, let's actually do the computations now. We're going to combine the factor fact and continuity. So in this example, I take the limit as x goes to 5 of that expression. I can use the factor fact to remove the common factors in the numerator and the denominator. Now I'm left with the function x plus 7. That's a nice calculus function. It's nice and continuous. And in particular, the number 5 is in the domain of that function. So I can plug in 5, nothing crazy happens, and I get just the number 12, so that is the answer. Here's another example. The limit as x goes to 2 of that expression. Well, I want to see if there are common factors on the top and the bottom, so let's factor the numerator and the denominator. That's just algebra. Oh, I do see some common factors. X minus 2 appears in both the numerator and denominator. We can cancel those out. I haven't taken the limit yet. I've just simplified the limit problem. That's important to notice when we use the factor fact. I'm not actually computing the limit. I'm just simplifying the limit problem. But now this is a simpler problem. Can I plug in at this point? Can I plug in a 2 and get a reasonable number out? And I can. since I can, then plugging in gives me the answer to that limit problem. And the answer in this case is -1/2. The next two examples are some slightly more complicated problems, but we use the same ideas. How would we figure out this limit? The limit as x goes to 1 of the square root of x minus 1 divided by x minus 1. As it is, I don't really see a common factor on the top and the bottom. So we can do some tricks, and it really is just kind of a trick, in order to manipulate that fraction, in order to turn it into an expression that does have common factors on the top and the bottom. Oh, before I get too far, my first step should always be, let's just try to plug it in, because if I really can plug in 1, then heck, that's my answer. But if I do try to plug in 1, I get 0 in the denominator, so no, that won't work. Alright, well, here's the trick on this problem. Whenever you have an expression like the square root of a plus b, there's something called its conjugate, and the conjugate of that expression is the square root of a minus b. So the trick is, if you have a square root expression, multiply the top and the bottom by its conjugate. So the square root of x plus 1 and the square root of x plus 1. So the square root of x plus 1 over the square root of x plus 1 really is just 1. So I'm not changing the problem, I'm just changing how the problem looks. So this becomes the limit as x goes to 1. And what happens when I expand the top? So I use FOIL to multiply those two together, and I get x plus the square root of x minus the square root of x, so they fall away, minus 1. And this is really why we multiply by the conjugate. It just simplifies things so nicely. In the denominator, let me just leave that in factored form. X minus 1 times the square root of x plus 1. And I left it factored because, oh, I really see there's a common factor of x minus 1 in the top and the bottom. So the problem simplifies to the limit as x approaches 1 of 1 over the square root of x plus 1. Now, can I plug in 1 and get an answer that is a number? Yes. 1 over the square root of 1 plus 1, which is 1/2, and there's my answer. Here's another problem that's a little bit tricky. Compute the limit as h goes to 0 of 1 over 5 plus h minus 1/5 all over h. Alright, the first step is try to plug in. Can I plug in and get a number out? And the answer is no, because if I plug in 0, I get the 0 in the denominator, and it's undefined. Okay, so now I see, can I use the factor fact? Well, I don't see a common factor on the top and the bottom now, but maybe if I do some algebra to simplify that guy fully, I will have common factors that I can cancel, and that's where we're going. So do this for me. Pause the video for now, gather together all of your algebra skills, and simplify that fraction as far as you can, and see what you end up with. Unpause the video when you're ready to check your solution. Alright, I will now algebraically simplify that fraction. This dividing by h, I'm going to pull that out as a 1 over h factor times, let's see, 1 over 5 plus h minus 1/5, something like that. Now, I want to simplify the 1 over 5 plus h minus 1/5, so I need a common denominator. So on the left, I'll multiply that by 5 over 5. On the right, I'll multiply that by 5 plus h over 5 plus h. So we end up with 1 over h times, and the left fraction looks like 5 over 5 times 5 plus h. And I'm subtracting the fraction 5 plus h over 5 times 5 plus h. And at this point, this is where 80% of calculus students make an algebra mistake. Are you one of the 20% or one of the 80%? Do you see what the trouble is? Here we go. The trouble is, when I subtract, I'm subtracting the quantity 5 plus h. I'm not just subtracting 5. So 5 minus the quantity 5 plus h gives me 5 minus 5 minus h. It's that second minus that people miss. This is over 5 times 5 plus h. Alright, so what is that really? This is 1 over h times a negative h. 5 times 5 plus h. And let's just go ahead and make that one nice fraction. We'll call that negative h over h times 5 times 5 plus h. And so by simplifying that fraction, the fraction I started off with originally, by simplifying that fraction, oh, I really did end up with something that has a common factor on the top and bottom. All right, so all of this work has just been simplifying the fraction. Let's return to the limit problem. The limit as h goes to 0 of 1 over 5 plus h minus 1/5 all over h equals, now put in that simplified fraction, the limit as h goes to 0 of negative h over h times 5 plus h. I can use my factor fact. Let's cancel those h's. I get the limit as h goes to 0 of, maybe we'll call that negative 1 divided by 5 times 5 plus h. And now that I've simplified, now that I've canceled common factors, I ask myself the question again, can I plug in this value of h and get out a number as an answer? And in this case, I can. When h is 0 now, this whole fraction turns into negative 1 over 5 times 5. So the answer is negative 1/25. And that is it. So there is the answer to our limit problem. I want to wrap up this section by talking about limit laws. This is a little bit of theory. So previously I told you that for 99% of functions, you can evaluate the limit simply by plugging in if the limit exists. Well, if you want something that's 100% true, we have to follow the limit laws. And the limit laws tell us, for example, things like if I have two functions that are being added together and I want to take the limit of those two functions, then I can take the limit of each function individually and add those answers together. The limit laws really give us a way to break down limits into simpler problems. Like this sum law an example of that might look like this. The limit as x approaches 3 of the function x squared plus x, that can be broken down into two simpler limit problems. The limit as x approaches 3 of x squared plus the limit as x approaches 3 of x. And there's a difference rule that's pretty similar. I can use subtraction as well. The constant multiple rule comes up a lot. So an example of that might be the limit as x approaches 3 of maybe the expression 5x is 5 times, so 5 is acting as the constant multiple, 5 times the limit as x approaches 3 of x. The product rule comes up often, so the limit of a product is the product of those two limits, and the quotient rule comes up pretty often. If I have a fraction, f of x over g of x, then I can take the limit of that fraction just by taking the limit of the top and the limit of the bottom, but there is this caveat here, provided that the denominator doesn't actually turn into 0. We've done, in this lesson, we've done limits of fractions, and we've seen that the denominator is often 0. And when that denominator is 0, we can't just split up the top and the bottom. We have to find some other way of solving the problem, like using the factor fact, like canceling common factors. All right, let me do one example that shows using the limit laws. What limit laws are needed if we were to compute the limit as x goes to 2 of this expression here? Now, my previous work would tell me, let's just plug it in, right? If I can just plug in 2 and I get a number out, then that's the answer. And you can see right away, yeah, if you plug in 2, you're going to get just some number out as your answer, so you can do that. But we're being strict, we're being 100% true to mathematics. And so let's follow these limit laws carefully and see what we are actually using to compute this limit. So the first thing we might do is use the quotient rule, where I can separate the limit on the top and the bottom, and I do know that I'm allowed to do this because when I look at the bottom and the limit as x goes to 2 of x, that won't be 0. The limit as x goes to 2 of x is just simply 2, right? So I'm safe to do that. But now let's work on that numerator. We'll split up the limit among those three terms. So the limit of x to the 4 plus 3x minus 1 is the limit of x to the 4 plus the limit of 3x minus the limit of 1. And so I used my sum and difference rules to split the limit that way. What will I do next? I'm going to simplify my x to the 4 limit, and I will simplify the 3x limit. And so it turns out that this power can come on the outside, and I can take simply the limit of x and raise that to the 4th. And here I see my constant multiple rule, that 3, that constant multiple, can come out front. And so I've used the power rule and the constant multiple rule. So just a little bit of theory here. These limit laws are things that always do hold true, and I can compute and simplify limits this way if I really need to. All right, so we have talked about techniques for computing limits, the importance of canceling common factors to produce a simpler problem that has the same answer, and we've seen some tricky examples, like with this square root in this fraction, where the problem that's given to you doesn't look like it has common factors right away, but with some algebra, and really being careful with algebra, we can put it into an expression where I can cancel common factors and find the solution. All right, so that's what I have to say about 2.3. Good luck with your computing limits.